Okay then. Well, so today and next time, it's we had set aside a couple of lectures for recap and exercises and whatever. So basically, what I wanted to do was, we could do exercise. We could. I wanted to ask you in particular if you have anything you want to revise or questions, particular questions, topics that you would like to get more into or whatever. So any requests on this point, even from, of course, from people online? Question. Can we go through different methods for SciPy minimize? Okay, well, yes and no, in the sense, it's a good question, but let's see. Oh, well, I suppose I should. What they can be used, when they can be useful, etc. Yeah, okay, so first of all, I suppose I should share my screen, so let me do that. From here. Okay. Okay, so the minimize method. Okay. Well, it's not really. So it's really a little bit outside of the scope of this course because there are a few methods. Yes, a second. I mean, these two basically are ones that are variants in a sense of what we've seen, more sophisticated variants. Now, many of the others are for constraint optimization, which we haven't seen. In fact, where is it? Oh, yeah. So you see, the explanations are here, and well, I mean, you cannot really do justice to exactly when you should use, say, BFGS compared to these, in the sense that it becomes really subtle and you need to read the references, essentially. So it's a research area, so to speak. Probably, in most cases, nobody even knows which one would be better a priori. Okay, this is one of those situations in which there are two or more, actually many more, methods which are competing. Most are good. Sometimes one is better than the other in some circumstances. And it's often very, very hard to pinpoint exactly what circumstances those are. This happens all the time in these kind of situations. So, for example, yeah, I mean, what I'm trying to convey is that you'll see this also in the next semester in machine learning. When there are similar situations, many topics in machine learning involve optimization, some optimization process, and basically all those cases, the optimizations are about non-convex functions, so functions which have lots of local minima and large number of variables and so on. For any specific situations, there are several competing methods, and telling which exactly is better suited to any situation is basically it's very, very difficult. That's what I'm saying. So, yeah, I can't really give an explanation that goes beyond just, well, use the standard ones and the main point is whether they use the Hessian or not. Essentially, that's the main. The main and when you are solving a constraint optimization problem or not. So whether you are given these constraints, something that tells you, for example, the variable must be positive or something like that, or some combination of variables must be below some linear combination of those, or something like that. Beyond that is it's really, I mean, one would need an entire course in a sense to get through this. There was a question or a comment? Or... Sorry. Oh. Okay, later. Sorry, you were saying, I just cannot hear very well because of the mask now. Yeah. Ah, yes. Yeah. The one of the first exercises in the dynamic programming part. Yeah. Okay, so let me so the question is about these two. Okay, let's pick this one, I guess, or I don't know. I don't know which one you prefer. Okay, so here's the code. Are you referring to the code or to the exam text? The code. So, okay, let me just bring up the, where was it? Okay, so no, yeah, this one. Okay, so which part of the code? The functions. Ah, this one. Field and gengraph like. Ah, I see. Okay, so good. Okay, so the question is basically what are these functions doing? Okay. Okay, so, well, this is an auxiliary function. This here, so this is just auxiliary, but it's a small piece of code. So, well, I guess this is not even needed. If there's full, right? Yeah, okay. So, well, first of all, this function here is probably not needed. It was just for demonstration, or maybe. So, there's this function npfull, which does basically the same. Except you don't specify the type. Okay, so this is just creating a vector, really, of length n, filled with some value x, and optionally constraining it to some type. So just to see what this is doing, you can give a length like 5, a value like 3.14, and you don't specify the type, that's float by default, and this gives you just a vector of length 5 and this type. Okay, and I suppose you can even give a tuple, so 5, 3. Yeah, you can create a matrix or whatever other array. Okay, so nothing really too strange here. You can do the same with full, as I was saying. So if you do np.full, it's the same. In this particular case, exactly the same. Here, what is done is it first allocates an array and then it fills it. This does it all in one step. I don't think that you can specify the type. Maybe I don't know. Yes, you can. So yeah, so basically this function here, I should make a note. This is not really useful in the sense that there's this other function. Now, gengraph-like is the main function. Now, gengraph-like is something. Let's see it in action first, so that we can have an example. Gengraph-like. What are the graph names? Let's pick one, the test ones. So there's just one. No, there's. Well, there's this one, this graph here, but it's completely trivial. So let's use test G1. So you have test G1, and then as an argument, you say, well, the values to use for the first one and then the rest, let's use the defaults for now and see what happens. Okay, so this is something that creates, first of all, it creates a list of the same, so it's supposed to mimic the structure of the graph. Like, so it's a list of 1D arrays, and you can see here that there's the graph, test G1. Test G1 is a graph with 5 layers, 1, 2, 3, so actually 1, 2, 3, 4. It's 5 layers, so there are 4 matrices, because the matrices represent the connections in between. So this is given a graph, you can figure out the number of actual layers, which is just the number of these items plus 1, and also you can figure out the size of each layer by just looking at the size of the matrices. So this matrix here tells you, well, that the input layer's length 3 and the output layer's length 2. Sorry, 3 also, because it's 3 by 3, right? I guess. This one here has input size 3 and output size 2, and this one is 2 times 1. So correspondingly, you see the first one is always 1 in this example, and the last one is always length 1. This one is 3 by 3, so it tells you that this one is 3 and the other is 3. This one is 3 by 2, so it's 3 and then 2. And this one is 2 by 1, which you already knew. Okay, so this is the how the lengths are figured out. And then essentially you want to have some quantity associated to each node. So okay, so what was the question exactly then? The syntax. Okay, so the syntax is well, this field, as we've just seen, this gives you an array of length 1, because there's only one node at the beginning. And so, okay, and filled with some value that you give, which is 0 right now, and with some given type, which is float in this case. Okay, so this one here is an array, and then you put that into a list. So it's a list with one array in the middle. Now, here, this one is a list comprehension. Okay, so this tells you, look through the graph G, so go through all the elements of G, which are individual arrays, you see. And so GL is one of the arrays, it's one layer of the graph. And for each of those, just look at, take the number of columns, so it would be 3, 3, 2, 1. Take the number of columns, then columns, sorry, and then create a vector of that length, so 3, 3, 2, 1, and then put all of those in a list. So this creates the list, this list here, essentially, with these elements, and then concatenate them together. Now, this plus here is operating on lists, not on arrays. So this might be confusing. In NP, if you try to sum two arrays, you get the array width of the sums. In Python lists, if you take the sum of the lists, they just concatenate. So maybe this was the origin of the confusion, I guess. So this just takes one list and with one element and attaches it to another list with whatever, how many elements are needed. Yes, so? No. It's so the question is, what if I do it essentially by starting with a list of one and then appending one element at a time? No, that's not more inefficient. That's maybe even very slightly more efficient. It's basically the same. It's basically the same. This one was just to write everything in one line instead of writing a for loop. But here really there are no matters of efficiency because list comprehensions in regular Python are just a way to write a for loop with fewer characters. There's no what do you say? There's no performance concern in this case at all. There are no. It's the same thing. It's not like when you use NumPy and there's broadcasting, and broadcasting is faster because it's using specialized internal routines. This one is just syntax. Okay, so yeah, doing it is perfectly fine. Okay, there are other questions about this or this exercise? No? There's a question, how could have we used boundaries with minimize? Okay, so back to minimize. Okay, so in minimize, if you go through the documentation, there's this option, constraints. Okay, so here it tells you that constraint should be one of these two, basically one constraint or dict or a list of those. Okay, so these are only useful for some particular methods, as you can see, which are for constraint optimization. Then it says that you could use one of these, in particular linear constraint. I suppose it's the easiest one. This explains you the mathematical form that the constraint can take, which, I mean, you have its mathematical form translated into Python, essentially. What this means is, suppose that you have a matrix A, and suppose that you have a vector X, and then LB and UB are also both vectors, and they're also both optional. So if you want, let's see, maybe an example is easier. Let's see if I manage to do one on the fly. This one here. Okay, so, of course. Yeah, okay. So, where is it? So what that is saying is LB, which is a vector, less equal than A times X, where A is a matrix and X is a vector. And when I say A times X, I mean vector, standard matrix vector multiplication. So let's say L is a vector, and then it says less than or equal to A times X, where X is a vector and A is a matrix. Okay, and this is supposed to be L is given, and A is given, and X, of course, is the variable, the optimization variable, or variables if you want to see them as multiple variables. Okay, so this is what he's saying. So for example, just a very trivial case could be in one dimension. If you have one-dimensional optimization, then that's like, I mean, you can write L as a vector of length 1, A is a 1 times 1 matrix, X, your variable X would be a vector of length 1. So this would be something like a X, so right where Now everything here is real. And so, for example, this is ax minus L greater or equal than 0, which, well, I mean, in this case, you can also rewrite, actually, not all the cases. There's an arbitrary common factor here that you can eliminate. I mean, assuming both A and L are non, in particular, let's assume that A is non-zero, because otherwise nothing would make sense. Then this would be like saying this. And so it just says, okay, now your variable x must be greater or equal than something. Sorry. Yeah, must be greater or equal than some value. In the two-dimensional case, suppose that the simplest case is when your matrix A is something like this. It's diagonal. And, well, your L, let's say, is L0, L1. And then the expression above becomes L0 less equal than A00 x0, L1 less equal than A11 x1. So this is just like saying you have two independent constraints on each variable. So for example, if you want positive variables, well, in general, this is expressing constraints like something like this, right? Saying, okay, you need to be over there. And well, if you think about it and do some experiments, if you put in some non-diagonal terms in the matrix A, then those lines there, they could just be not parallel to the axis. So you can create, let's say, different shapes, because they would then, the terms would involve linear combination of x0 and x1, which is just lines which are not parallel to the axis. Okay, and of course with the upper bound is the same, it's just the reverse. And so if you have both, then you could say, well, my variables must be larger than some value and smaller than others. So you could create, for example, a box here. You could say, okay, these two for lower bounds and upper bounds, and so you can constrain your variables in a box. And with a diagonal matrix, the box could be with lines parallel, with the sides parallel to the axis, and otherwise you could create slanted boxes and so on. And so you see, you just need to create this object here. You need to import from SciPy optimized linear constraint, and then provide the matrix, and then provide the lower bound and upper bound. And essentially, this is optional. This tells you whether, basically, what does it mean keep feasible? That means, is this constraint really rigid in a sense? So is everything, am I considering that anything outside of this constraint is totally forbidden? Maybe because if I try to go outside, my function would break completely. Or is it just that the function could be defined outside, but I, for my own reasons, want to get a solution inside some particular area? So it's like saying, so this second situation would be something like, suppose that your function is, I don't know, something like this, okay, whatever, and you say, okay, the function could be, I don't know, a polynomial. Oh, you don't see it. Could be a polynomial of, I don't know, whatever order. In this case, let's say a polynomial of order 8, whatever. And then you say, what's the minimum? Unconstrained is this. So the function is defined everywhere, but now you say, no, I want the positive, I want to constrain only to get to the positive region, and then the minimum would be this one. But so if in a situation like this, then you can also say keep feasible false, meaning that you can allow the algorithm to go outside as long as it gets back in at some point, as long as the result is inside the allowed region. Instead, if you have a situation in which your function is not even defined on the negative axis, say a logarithm, you have log x in the middle somewhere, or something like that, or square root of x, then you would say, no, keep feasible true, because I really don't want to get out of that. And that's it. And then so you create an object like that, which expresses this, which expresses a geometrical constraint, and you just give it to this option. As long as you're using this function here. There's also nonlinear constraint, which, I mean, it's nearly the same, but instead of a linear function, you have a generic function that you need to provide yourselves. Yeah. And, well, there's also dictionaries here, and this is, you can, this is more complicated. I don't think it comes up really often, but in any case, the idea is sort of similar. Let's ignore Jacobian. It's just that you give a function that defines the constraint, and this works more or less like this, essentially. But it only expresses, now you can only express one of these two, say. But, so say, for example, you want to express this one here, then you would use inequality here and give a function that you want to represent, and that's it. If you want to express the other inequality, you should just reverse the signs of both terms and just transform it into, so this would be like, in order to transform this expression here in an expression like this, you just take the negative of both arguments. So that's just it. And so because you can provide more than one constraint, you can provide a list, actually, of these dictionaries, each dictionary containing these keys. Well, at that point, you can give how many constraints you want of whatever form you want. Okay, hope this answers the question. The way, by far, the most common case is using a linear constraint kind, but okay. Any other questions? Yes? Yeah. Okay, good. So the question, for those at home, is about Floyd-Warshall, and it's about the part that I gave you after the lecture, and it's the part about the broadcasting version. Okay, yeah, which I didn't get around to explain. So it's, I mean, I was kind of expecting this because that's a tricky piece of code, but let's look at it. It's dynamic programming, Floyd-Warshall. Okay, so it's the final, I guess. I should open it from here. I think I should open it. No, this, yes, Floyd-Warshall. Okay, so let's see. Yeah. Let's see. So, well, I'm not sure if it really, if it could help here. Let me try something. Maybe it's two different V3. Yeah. Let's see. No. No, V3 is already the broadcasting version. It has just tasks. Okay, so maybe V2. Okay, well, yeah. Okay, so this at least shows you at a glance what we changed. Now, let's go for a second, because of all these lines. We need to be somewhat familiar with the structure of the code already, so let's review that for a second. So here, this is the original version, I mean, the one which doesn't use broadcasting. You have a matrix W, square to the array, which represents the weights of the graph. And then you have this R, which represents the costs at each iteration, where at each iteration you allow one more node in the as a possible intermediary. And then there are these, so there's also pred, the matrix which records for every node which one is the optimal antecedent for each. So we, in the final optimal path from I to j, consider what is the predecessor of j there, which node is the one that comes before j. This is what pred encodes, and this is the main loop of the thing. And main loop, no, this is just the initialization of this pred, because you want to initialize it as just a direct connection from I to j, so saying that j is directly connected to I here, if the link exists, and if the link doesn't exist, then j is not connected to anything. And then this is the forward pass, in which this is the iterative steps, and these other two for loops are just basically to update the whole matrix. And so you have k times the update of the whole n by n matrix. Okay, so this is the structure of the code. And now, if you look at what's happened here, well, this is just argument checks. So ignore that. Okay, not. Sure. I'm hoping. Let's see if I can. Apparently not. I'm sorry. Okay, we will review this. This is just to tell that really, let's see, we'll review it in detail, but this is just to show that all of these initialization here, this was the part, this part here. So all of that has gone, essentially, this part here. And then in the forward pass, you see the k, this one stays here, and everything else has been transformed. So this is just to show the structure of the changes. And everything, all the rest of the code is unchanged. Okay, so this affects only these parts here. Now, I want to point out, before we go into the details, I want to point out that this is more or less a pretty general feature, that in dynamic programming, you have some loop, some main forward pass, and that main forward pass, this would be this one, k, for k in range. That forward pass, you can hardly use broadcasting for that. Why? Because it's typical, almost never, unless you have an absolutely trivial problem that doesn't even need dynamic programming. Why I'm saying that? Just at the structural level, because in dynamic programming, you have the next computation depends on what you did before. Okay, so every iteration of the dynamic programming is defined by a recursive relation, and but you solve that iteratively in the bottom-up approach. And anytime you do that, the next step depends on what you did in the steps before. And this does not go well with broadcasting, because broadcasting is useful when you can do several things in parallel, essentially. Okay. So this outer for loop, you can almost never, you can basically never optimize it, use broadcasting with that. But the one inside, you often can. Okay, so this is just to say that the structure here is not, what this is showing is a common structure in dynamic programming. Now let's go through the detail. The detail here is, well, so having understood that essentially this for loop is unavoidable, you have other pairs of for loops here and pairs of for loops there, and this, you might say, well, maybe this can be done more quickly with broadcasting operations. And indeed, it's possible to do that. So here, and those are two separate things. Okay, so you can do them independently. So we look at them one at a time. Unless is the question specifically about one of the two? The second one. Okay, so in the second one, so let's see. Let's remind ourselves what the second one does. Well, I guess that, okay, the second one is doing two things at once. It goes through the whole table of positions, and then for each one, it just computes a new value, and sometimes, possibly, depending on the new value compared to the old ones, it updates the value at some position, and it also updates the pred matrix. Now, in order to understand how to broadcast over this, it's best to simplify our lives at the beginning and just ignore this second part here. Okay, so we start by checking, can we optimize something like this? Okay, or rather, something like this, sorry. So in order to do that, maybe the best thing would be to maybe even have a little something on the side, I don't know, some test case on the side, let's see. Okay, let me try. So one could write a little script and then define n to be something like small number 5, just to see how things are going. Then observe that now we're here, we took this from inside the for loop, and so k is fixed here. So let's define, I don't know, some value k, okay? And now here it also says that r is undefined. So let's just create a random r of size n by n. Okay, and I think that this should be fine. And so, well, we are using random numbers, so let's use a seed. Whatever seed, doesn't matter. Okay, clear all the variables, maybe, or restart the kernel even just to, because I want to start from a clean slate, and just execute this code. Not me. Tuple object, what is it? Okay, yeah, always mix up the syntaxes. Good. So, okay, so now I have R. Now, one can say r.copy, and then R after, oh, well, maybe I could say R before and R after, I suppose. Okay, so let's see, R before, R after. Okay, so now we have this computation. And at this point, we would like to see if we can do the same with broadcasting. Now, here's the thing. Imagine if there was not this condition, essentially. If you had an even simpler situation, which goes like this. So let's simplify our lives again. J equal this one here. Okay, comment out this one. Okay, so now this situation here, you see, what is it doing? It's now at least things start, I hope, to look simpler here, in the sense that here k is fixed and this one is fixed as well. So what that's doing, what that is doing is something like this. You start with, let's say, R00, R01, R02, R10, R11, R12, something like this. Can you see that, hopefully? Okay, and then you are computing. The first one is R, and then suppose that K is equal to 2. I don't know, here. Okay? Anything. One value between 0 and 3. So the first one is R ik, so 0, 2, plus R kj, so k 0. And here you have R. So the structure is the same everywhere. It's R times. And so the k is here. Maybe I can even write k instead of 2, because it's fixed. So I have something like this, k in the second position, k in the first position. And here I have 0, 1, and here I have 0, 2. You see? And same here, R1k plus RK0, 1k plus RK1, R1k plus RK2, and, well, okay, RK0, R2k plus RK2, R2k plus RK2. Now, okay, first of all, at this point, you see, if you, or you would see, if you could, okay, this is the structure of the thing that we're trying to compute here. And you see that now this has the structure of the sum of two matrices. Right. Now, so you can now split out the two matrices. The first matrix is R0k, 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 R1k, 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 R2k. Okay, I think you can spot a pattern here. And here on the other side, I have RK0, RK0, RK0. You see I'm going through columns now. RK1, 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 RK2, RK2, RK2. Okay, now these are two matrices. Well, what is the first one? The first one is just essentially R0k, R0, oh, sorry. The first one, if you look at it, you can rewrite it as R0k, R1k, R2k, repeated in a sense, okay, times 3 if you want, okay, with the notation that I just came up with right now, okay, but it's repeated in this direction, and the other one is RK0, RK1, RK2. Now this one is a row which is repeated 3 times in this direction. And it so happens that if you actually have a column and a row like that, and you sum them up, the repetition is given to you by broadcasting automatically. So if you now try and check, you can check that, let's say, well, here you can say, well, R equal R before. Okay, so let's take the before matrix. And now K is equal to 3, we said. So let's see if we can take this one. What is this one? Is the matrix R with all the rows are changing and K is fixed. And so here you translate it with R. The rows are changing and K is fixed. Okay, so this one here. This one here, it looks like a row vector, right? I mean, it's one-dimensional because we have thrown out one dimension, even though we are going through the row, we have fixed one column and going through the rows. The syntax of NumPy takes that and discards all the dimension except one, and therefore it represents it as a row vector. We want to bring it back into a column, just like here, okay? Because it's the left one. We want to bring it back as a column, and therefore we need to reshape it. As how many rows? There are n rows and one column. So something like this. Okay, good. So you would think that this should work because that's the transposition operator, but no. Okay, so this is a common issue with NumPy, an ongoing theme, because NumPy gives you mathematical operations, but they are defined in a weird, different way. Just like matrix multiplication in NumPy is defined in some sort of sloppy way, in which row vectors and column vectors are sometimes mixed. Transposition also is not defined it's not defined like in the mathematical world. The reason is that they want to have a transposition operator that works for any dimension of the array, any number of axes, and not just for the matrices. And therefore, what that operator .t actually does is it swaps, it reverses the axes. So in a matrix, you have 2 by 2 axes, just 2 by 3, and that swaps them. But in a vector, you have just one axe. And so it reverses it, and it doesn't change it. If you had a 3-dimensional thing, 2, 3, 7, for example, it would become 7, 3, 2. So it just reverses everything. And so it doesn't work for a single vector. But you can use this. I mean, it's a little bit ugly, but I mean, it's quite ugly, but it works. Okay, it works and it's fast. It's not, computationally, it's okay. And so now you have this here, okay, and the other one, and so we have got this. The other one is this one here, which is just the same, is R, in which you have fixed K, and you change the column. So the fixed row, and you change the column, it means take all the columns. And so this one here is this one. And now you sum them together. And so you take this one and this one here. Okay? And supposedly, this is exactly the same as R after. You see? So this is the same as these two. And so you can just have a check here. I mean, it's good to do something like this and say, okay, R after new, if you want, something like this. Or maybe just do it just like I did before. So R equal R before copy. So I'm restoring. So what I want to do is keep this code around and then repeat the operation in a different way and then check that I did everything okay, everything correctly. And because I'm doing operational on matrices, I need to keep to do explicit copies. Okay, so here I have my first one, and then I restore R, and then I do the new computation, let's say, okay, like that. And then you want to say assert. Well, in this case, we expect them to be actually equal. So R equal to R after, not equal. So if you do this, it doesn't really work. Why? Why doesn't it work like this? Anyone? It broadcasts, yes. Yeah. So as usual, I mean, this equality operator is overloaded, so you should need array equal. Array equal of these two. And you run the code, and it's not. But it did look pretty much the same. So maybe Ah, no, there's an error here. Something, what happened in the last line? There's something wrong. Ah, okay. Okay, so it's good up to here, but the last one is wrong. What did I miss? What did I miss exactly? There must be some sort of stupid mistake. K is 3. Ah, which is out of, no. Yes, K is 3. So, okay. What did I miss? Why is the last line not coming out correctly? The last row and last column. Reshape. So, for example, this, well, the last element here should indeed be, okay, let's, because key is neither the last row nor the last column are modified. No, but this goes through everything, including the last row and column, and so this should modify that. So if I say this and say for 4, well, the last element in the matrix should be 4, 3 plus R 3, 4, essentially, which is, this one is wrong. Why is it wrong? What happened here? Sorry again. This one here is coming out, it's impossible. It's a sum of 2. Maybe I did something here. I suppose. Right. I think I should have used this. I think the problem here is this one. Yeah. Okay. I think no. Before OK. Is it this one? Yes. Okay. Yeah. So yeah, I was. This translation is more complicated than I remembered. The reason is that we removed this one here, but essentially, I mean, the argument stays the same. The code was problematic because I was using the same R on the left and the right inside the loop. Inside the loop, R was getting modified, and in later positions at the loop, it was using the updated, the modified value of the matrix instead of the original one. Okay, so this is not really a problem if you have this condition and you're going to the Floyd-Warshall algorithm, but it's a problem in comparing this expression with this one here. And in particular, what I showed here is an operation that indeed is based on the old values of the matrix and then computes all of the new values of the matrix. And then only at the end it overrides them. So now this test works. Okay. Okay. So now we are on, say, solid ground, luckily. Okay. Now what about the rest? So if I wanted to do this instead, now let's recomplicate things again. So I comment out this one, and I'm using before, just to before. Okay, so now, what about this one? Well, here I'm not doing the computation. It's similar. I have this side here. It's the same as this one. But then this is for position ij. I compute just the same values as I was doing before, but instead of overwriting R all the time, I just do it when the new value is less than what I had before. Now, only in that case, I override the value. So what that means? What does that mean? It means, let's look at still look at this version here for a second. It means that now you have R before, okay, is something, R after is something. Now, you see, this after here is the new value, and you compare it to this value here, and it's smaller. And so it should actually get to override this one. It's actually better. This one here, for example, is worse than what you had before. This one here is worse than what you had before. This one here is worse. This one here is better, and so on. So you can go, now you have done the computation all in one line, like this, and now you could compare, say, the new matrix and the old one, element by element, and say, in which case I should have applied this operation here, in which case I should have updated the matrix. And so you can do this in bulk. So you first do the whole new matrix in bulk, and then do the computation, the comparison, this if operation, essentially. You do that, not the if operation, this less than operation. That operation, you do that in bulk. Meaning you do that for the whole matrix. So here you have R new, and then you can say R new, when is it less than R? And so this, you can call it a mask. Okay, this should still come out true. Okay, but now I have this mask. And you see this mask, I mean, just because they're doing this comparison, tells me, I mean, look at the first row, it's just what we were saying. This one is okay, so this one is smaller, this one is larger, 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 smaller. And so you get true, false, false, true. Okay. Now, why is this useful? Because also with masks, you can do assignments in bulk. So you can use them in indexing. And in particular, you can say R of mask equals R new of mask. Okay, so this means, okay, now change the content of R, override them using the contents of R new, but only at certain positions. Those where the mask is true. All right? So here, the mask is true at only some positions. And so this update actually will only affect 1, 2, 3, 4, 5, 6 positions. And it will only, so it will take this matrix here and overwrite it with the other one, but only at this position here, this position here, where you see it's better. I don't know where was the other one, but in any case, this one here is better. Okay, here there was another one here, I guess. So just these positions. And this supposedly should be the same as this one. Hopefully. And no, it isn't. Let me see. So here we have, not R new, it's R. Good. Okay, so now I have the previous computation based on 4 loops and the new computation based on these 3 broadcasted lines. Okay, so clear so far? Yeah.
Why do we need to put the left on the first array also?
On the left and on the right?
Yes.
Well, because, okay, yeah, good. So because if you didn't, look at, okay, this is our new mask. Actually, our new mask, what it does is it actually gives the elements, it's just 6 elements in this case. And so you cannot, on the left side, you would have a whole matrix. So you need to say, okay, the corresponding elements in those matrix, in that matrix. Okay. So now the final thing is, well, what about, I mean, this was, we are coming out up to the conclusion. What about the pred? So originally, pred was like this. Okay, so now let's also say pred is equal to something, doesn't matter, random dot rand, well, rand int, let's say between 0 and n, I guess, and size equal n by n. Let's see. Okay, this is a matrix of some kind of integers. Good, now we have this line here that we had been ignoring before. So here, so I do the same, pred before equal pred dot copy, and here I have pred after equal pred dot copy. Good. So you can compare, let's see, pred before and pred after. Okay, now pred before and pred after. Well, of course, this is only going to change anything under the same condition as this one here. And so in terms of the matrix, you see only this one has changed, this one has changed, you see this one. So what did change? The ones at the same positions here. This one, this one, this one, this one, and this one, and this one. So these 6 positions are the only ones which have changed, right? Not only in the R matrix, but also in the pred matrix, because they are only updated under exactly the same condition. So that suggests that we could do something of the form like this, provided we can compute pred new, right? So that suggests that you can use exactly the same trick and with the same mask. We already have the mask. So having said that, we need to compute pred new. Now, how do you compute pred new? Well, you basically, you think of the same kind of, it's the same kind of reasoning as before. Imagine if there was no if condition. So imagine if you wanted to compute it all. So all this, what would that look like? So that would look like this, something like this. So pred ij equal pred, if you want, pred before. Okay? So just to be extra sure. So you would have something like this. Okay? And now observe what's the structure of that. Well, just like we did pen and paper here, you can say again k equal 2 or something. You have your matrix spread, and that's something that looks like, I'm just using, sorry, you can see that. Okay, P00, P01, P02, P10, P11, P12, P20, P21, P22. Okay, now you say, okay, now what is the new matrix if I changed every ij with kj? Well, that would mean that the new matrix should look something like this. P kj, so k0, pk1, pk2. Now pk0 here also, pk1, pk2, pk0, pk1, and pk2. Good? So the left one is the old one, the right one is the new one, if we updated every single entry. Now the right one is, of course, pk0, pk1, and pk2, repeated again with this 3 times, okay, like that. But this time we're not doing a sum operation or any operation, so you cannot rely on automatic broadcasting like before. You need to do this explicitly. You need to say, okay, Nate, take that vector, multiply it 3 times, make a matrix out of that. So in order to do that, yes, you can. That's a trick. That's a perfectly valid trick. So yeah. Well, not sum a column, multiply by a column of ones. Or sum a column of zeros. Yeah. Okay, so that's valid. But there's also, for this case, the function repeat, which, I mean, it does the same, and it's more explicit in a sense. And also, it doesn't really do an operation. I mean, with some, okay, it doesn't really matter too much. But if you sum a vector of ones, then you need to allocate the vector and then actually compute the summation element by element. It's just an additional useless operation that the CPU has to do for no real reason. So let's just do a copy, which is cheaper. It saves you 1 CPU operation per line. So you take pred and you say, okay, k is fixed, and then the row, this is fixed, and this is, so this is, and this is variable, so this is our array. And then you say np dot repeat of pred k colon. Okay, and now repeat, you see it says how many times you should repeat and along what axis. So how many times you should repeat? Well, that's n. That's easy. And then if you don't specify the axis, however, that just gives you this, which is, you can see it as repeated every element n times. We don't want that. We want to repeat them along some axis. Well, axis 0, no, not axis 0. Axis 1, no. Okay, so it seems like we are going nowhere. What's the problem here? The problem is that we have our vector, and we would like to repeat it along this axis here, but that axis does not exist in the vector because the vector has only one axis, which is this one. So you reshape it first, you make it a matrix, and then now you have the 2 axes. So you say first pred k dot reshape. We want a vector matrix, so 1 row and n columns. And now this, again, axis 0. Now this works, okay? Because it's along axis 0, which is the rows. Repeat along the rows, this row column, the row matrix along the rows, n times. Well, it has the same result, but the reshape is cheap. The reshape is just reinterpreting the memory in a different way. So it just changes to integers. So, and also, well, repeat is performing copies, so that costs you some, but at least it doesn't do mathematical operations. And again, doing the summation is a perfectly valid way to do it. It's not really that important. Okay, so now we should have something that this should be our pred new, hopefully. We didn't mistake anything. This is pred new. Now we have this. So this was just for our comments. This is like that. And we can hopefully have that this here should work. Let's see. Oh, a miracle. Okay. So you have, now we have this. And we can take these operations. And so all of this now we have substituted with this. So you can go here and say all of these you can substitute with those commands, which you see here. This is new R, the mask. This is changing the mask. The new pred is exactly what I wrote, and then you change pred. Okay? And well, the initialization of pred, it's sort of similar, except that in that particular case, if you look at the code, I mean, if you look at this code here, and you want to say, okay, let me try to broadcast that, the trick is still the same in the sense that, first of all, you pretend like this if was not there. So pretend like you are doing this thing here for all I and j. And so create a matrix. Pretend that if you think about how that would look like, it would look like a matrix like this. And so that would be a range along the column this time, and you want to repeat it along the columns. So in this case, you reshape it as in the shape of a column and repeat it n times along the direction of the column. See? You just take this for loop, ignore the if at the beginning, look at the structure of pred, just like we did, pen and paper. It comes out as something like this, and then you figure out, okay, I need to take a row which contains 0, 1, 2, 3, 4, and so on, and just put them in a column and repeat it. And that's then the line. Sorry, could you repeat the meaning of a range in this case? A range is just a function that's the corresponding, I mean, the counterpart of range. So in regular Python, you have range 5, which gives you an object. But if you expand it, that's it. And a range 5, it's the same, essentially, at least at this level, except that it creates an array, a NumPy array, instead of a range. And that's it. Now, with a NumPy array, then you can use NumPy operations like reshape, broadcast, repeat, and so on. Okay. Well, the other difference for a range is that you can create ranges with floating point values, which you wouldn't be able to do in regular Python. You can even, I think, do something like this. Yeah, so create, you see, floating point ranges, starting from 2.5 up to 5 excluded in steps of 0.5. If you try to do that with a regular Python range, it doesn't work, because that only accepts integers. Okay. Any other questions? Anything obscure? I guess this was one of the most delicate points. To what documents exactly do we have access during the exam? Okay. I will give you the whole of the Python documentation. So this annoying thing, okay, it's right. Okay, so basically Python docs there. Okay, so all of this, whatever you can access from here, whatever you can search from here. Then also NumPy documentation. So I think I think this one. Well, essentially, you see there's HTML plus zip. So what I do is just this. I download this HTML version, the offline version of the documentation. Okay, now if you open it, it looks like this. So maybe, let's do this. I save it. Okay, then okay, sorry about that. Okay, so now you have, so I'll give you a zip file like that, essentially. Now, from that, you can extract it. You need, in order to look at it, you need to extract it. You're going to have access to a computer with Windows, but that's the same. You right-click and you say extract here or something. There's 7-zip, I guess. Now you get into that, and here you can double-click on index. Index is always the entry page for any website. Okay, index.html. It's any website starts with an index.html. You double-click on that, and you see now here I have in the browser the documentation at some position in my computer, and you can navigate through that. So this you will have, okay, during the exam. You will have this, the analogous thing for Python documentation, so the exact same thing. So all of this, except that you're going to be using it in, you need to just unzip it and then double-click on index, and then you will have the same thing here, like that. And the other thing I want to, I'll give you the minimize, this one here, essentially, the minimize page. Yeah, you can use whatever you want. Sorry? If you can have it. Yeah, you can. Absolutely. So the question is if you can have scrap paper, and the answer is yes. You can have scrap paper, you can have notes, you can have whatever. Sorry? Yes, it's open book. Yeah. So yeah, you have the documentation for minimize. I'm not giving the documentation for the full of SciPy because it's just too huge. It's, the zip file for that, the analogous zip file for SciPy, it's several megabytes, and it takes ages to unzip in the computer room. So you just have minimize, but that's all you need essentially. And that's it. This is the documentation you have. Okay. I really tried to book in advance before the exam, to book a session in the computer rooms, just so that you could see what it is, how are the computers and so on, and we could do some sort of simulation. I couldn't. All the regulations and other factors have prevented this possibility, but also, will the exam be a random topic or a combination of a few? Well, I think I gave the exam examples, so you can see, you have a sample of exams, and this exam is going to be, let's say, most similar for what regards length and the style of the theory questions. That's going to be most similar to the last two that were shorter than the rest, I think, because we have less time. So 1 hour. Yes, essentially. Yeah, more or less. I'm still trying to. These discussions go on. You have no idea. These discussions go on a lot, back and forth, a lot. I try to get more time, but we'll see. More or less 1 hour. 1 hour, between 1 hour and 1 hour and a half, let's say, something like that. Yeah. If you can, yeah, the flash pen, yeah. You can, so you can bring your own USB key with whatever codes and notes and whatever you want. You can, I mean, just make sure that they work with Windows. I mean, don't have a USB key formatted for Mac or something, because that's asking for trouble. Make sure of that. You can bring, as I said, for people used to different keyboards, you can set up the keyboard as the way you want, but if you want to see the layout or whatever, just bring your own. I mean, you can bring a USB keyboard. The USB should be the USB, the large one, the old one, the B version, USB B adapter, and there's no Bluetooth or anything, and that. Okay, anything else? So there's just 5 minutes left, so if anybody has any other questions, can we also bring notes on papers? Yes. So the idea here, so the general criterion is just that you do the exam on your own, without talking with people around you and without access to the internet or any means of communications to everyone else. For the rest, everything is allowed. I mean, that's my intention. Okay, whatever you want to bring. I don't care if that you memorize the documentation. Essentially, I care that you are able to parse it and look for it quickly if you need. That's it. Nothing more. Okay. So I don't think there are any. So just to conclude this, we are going to have the last lecture on Thursday. If you want to discuss among yourselves and would like to request some topics, please do. And so if you reach some sort of agreement or something with spread, please tell me at least a day in advance, so that maybe I can come prepared to do something in particular. Otherwise, we'll do it more or less like today, and so take it like this. I don't know, we can say go through one of the past exams, for example, or anything that you don't. So if you have a look at past exams, say for example, and there's something that you really don't know how to figure out, we can discuss that. Okay, that's it. I guess I'll stop the recording.